we found the correct address in the cache, then we are happy and get the data very quickly. If not, we need to fetch the data from memory and write it to the cache. And when we write something to the cache, usually we need to remove something else from the cache, and this is called cache replacement. And there are different options to select which line that should be overwritten. And the easiest choice is if we can find one with the valid equals false, since then we don't destroy anything useful. Otherwise we can take a random line. An alternative is to use if we keep track of which lines are used, then if we collect some statistics, we can keep track of that, and then we can avoid overwriting a cache line which is actively used. But for now, we just take a random line. Okay, and let's see how that will look. So if we found it, then we have already fetched the data and the load instruction has completed. But now we didn't find it. So we somehow select a row or an index into this cache array. And then we should check if this data is valid, because if it is, this cache needs to copy it back to ROM, to memory. And this is we can see that we really would only need to copy it back if it's not the same that is already in memory. So if we would extend this cache to keep track of if we have modified the data in the cache, then we could skip copying it back to memory if it was not modified. But in this cache, we don't do that. We just copy it back. And we want to have it as simple as possible for now. Okay, so when we have written back to memory, then we fetch the new data, and this is what takes time. It can take several hundred clock cycles. And doesn't it take the other also take a long time? Yes, it does, but usually the processor does not have to wait for this. In some multi-cores in parallel programs, they have to wait, but that is outside this course. It's in the multi-core programming course. What happens at the cache level. When we come to, so this is quick to just send away the data. We don't have to wait for it. But usually when the processor reads data from the cache, from the cache and didn't find it, so it has to read it from memory, then it is because the program wanted that data, and typically the program cannot do much without that data, so it will have to wait for the data. That for reads are much more they can cause more troubles than writes for performance. Okay, so once we got the data, we will put it in the cache. And the situation is similar for stores. So we just try to find it, and if we found it, then we overwrite the previous value of the data and leave this. Otherwise we have to select a row and copy to memory what was there if it was valid, and then overwrite this with our own data. So with the hope that we will read this data in the future, so that read will be faster than if we had not put it in the cache. So again, this loop, isn't it slow? No, it's not, because it doesn't exist. The hardware, as we can see here, and as I mentioned before, it's called comparators, and at most one of them will find the proper address and say it's here and provide the data if it was for a load. Okay, so if we look at the program that we had for this machine.c, namely the factorial program, it computes factorial for 5 and recursively. So there are 5 calls to factorial, and each one needs to save the parameter and the return address. So that is I mean, each call saves 2 words of memory, and also the main also saves the return address. So there are altogether in that program 11 writes. And then there are a number of reads, and most of the reads are for instructions. Well, maybe not most of them, but many of the reads are for instructions. I think it must be most. Okay, so let's see what happens if we increase the size of the cache. We have initially, with only 8 rows in the cache, we have 21 read hits and 0 write hits. If we make the cache much bigger, then the write hits still are 0. And the reason for that is that we save data when we make new function calls in new places in the stack. So we never reuse the data that we write, but some of the reads can enjoy read hits, but not all. And those which cannot are instruction fetches. Okay, so that's the explanation that I just gave. And some comments is that this cache is extremely small, and usually a cache which is on the same ship as the pipeline, it's perhaps 32 kilobyte or 64 kilobyte. And okay, we may be able to have 128 comparators, even if that's quite a lot, but having hundreds of them, or that is not the most best way to use the area of the ship. Okay, and we will see techniques to do that. To get better performance and exploit this locality better, but without wasting too much area of the ship on comparators.